In this video, I'm going to have a look at using the Matplotlib plotting library in Spyder. So let's launch Spyder. So we can import Matplotlib using the alias mpl. And if we just create a folder called Matplotlib tutorials, you don't want to use the folder name Matplotlib because this will cause confusion when you use your import. So if we import Matplotlib as mpl, and if I just change the variable explorer settings to view columns and modules, we can see that it's listed. So from mpl, we can have a look at the version. So we can use the data model attribute version, and this gives us the major, the minor, and the patch version. So in this case, it's 3.9.2. And generally, Matplotlib has a stable API, so unless the major version changes, what's outlined in this video should be applicable to likely your newer version of Matplotlib by the time you get around to watching this video. So the Matplotlib library has the data model attribute all defined, which is a list of identifiers. And recall when you type in from Matplotlib import star, you're essentially importing all the identifiers in this data model attribute list all. So it's generally bad practice to use a star import, but I've just done this so you can view the identifiers in the variable explorer. And I've used ChatGPT just to outline what each of the identifiers are. So we've essentially got attributes which give information. We've got color maps and color cycles. And then we've got some warnings and logging. And then we've got some configuration settings and backend settings. And then we've got recall parameters. So the Matplotlib library is actually compartmentalized into modules. So if we have a look at the data model attribute file, we can see the file location of the Matplotlib initialization file. And if we print this out to process the escape characters, we can get the full file path that we can copy and paste into Windows Explorer. So here you can see the initialization script file, but you can see that there's a large number of other script files, which are other modules. And then there's the folders, which each correspond to a module that contains multiple script files. So I can just use ChatGPT to give me a brief outline of all of these modules. And I'll just copy and paste the results to the left. So Matplotlib has interface modules, and the main interface module that you're going to use is PyPlot, which stands for Python plot. There was also MLab, which was essentially an interface module for MATLAB syntax, which Matplotlib was initially based upon, but this is deprecated. And if we scroll down through the other modules, you've essentially got a module for the figure, for the axis, for lines on the axis, and for other objects that you can place on a plot. So generally, we import the interface module, PyPlot. So if we just go into the Matplotlib folder, we see we've got this pyplot.py. So we import matplotlib.pyplot using the alias plt. And if I just go back into the folder where Matplotlib is installed and go up a level, we can see there's also this MPL toolkit. And this is generally used for, so this contains other modules which are used for example, for creating 3D plots. So the PyPlot namespace is pretty broad. Essentially, Matplotlib is based upon Python and also based upon NumPy. So there's a lot of things imported from Python standard libraries and from NumPy that are in the Matplotlib namespace. And these are used essentially under the hood to create objects such as graphs, but you're not going to want to use these within the Matplotlib namespace. So there's this function getPlot commands, and it will tell you the most commonly used plotting commands within PyPlot. And if we use ChatGPT just to give us a brief outline of these, we see we've got figure, which creates a new figure, and we've got figure creation base commands. We've also got axis creation commands, and then we've got figure level commands. And then we've got axis level commands that essentially carry out some sort of plot. And then we've got axis property commands. And then we've got some specialized plotting functions. So generally you create a figure, then you add an axis to the figure, and then you plot on the axis and you change some of the figure and axis properties. So that's the general workflow when you're creating a plot using Matplotlib. In order to plot, we're going to need some data, and the expected data structure is a NumPy array. So we're going to import NumPy as NP. NumPy is in the PyPlot namespace as well, but when we're using it as an end user, we generally import it directly. And I'm going to create these two basic arrays. So the X array and the Y array have the same number of data points. And if I run this code, I can view X and Y in the Variable Explorer. So X is the independent variable and Y is dependent on X. So Y is a function of X generally. And if I just move these over, what we're essentially going to do now is use Matplotlib using procedural programming. And this is similar to the syntax used for MATLAB. So if we highlight figure and press Ctrl and I, we can have a look at its documentation. So all the parameters here are optional, and if they're not assigned, they're going to be set to a default value. So we'll create a figure and then we'll create a subplot on the figure. And once again, we can have a look at its documentation. So the default is 1, 1, 1, which means we're going to create a single subplot on the figure. Now let's have a look at the plot command. And here we want to plot Y data with respect to X data. And if we go ahead and plot this, we'll see the plot in the plots pane as a static image. If we change the backend to Qt, notice that the plot displays in its own window. So unfortunately this window doesn't stay on top, so when I click something on in Spyder, it gets brought to the back. So I can use PowerToy settings to use this always on top. So I'm going to highlight the window and I'm going to press Control Windows and T, and now the window is going to be on top. So now that the window is on top, I can have a look at its essentially figure level properties. So this dialog box is actually shown behind this graph, so I need to press Control Windows and T again to bring this on top. And here we can see we've got figure level properties which we can change in the general user interface. So here we see the borders of essentially this black box and where they're positioned on the figure. So if I change these to 1 and 0, notice that the black box is now at the very edge of the figure. If I reset this, I can set it to a tight layout, and the tight layout is sometimes better when you've got title bars and you've got axis labels and so on. So now let's have a look at the axis level options. So we can set a title. We can change the minimum and maximum value for the x-axis and set an x label. We can do the same for the y-axis. Notice that we can change the scale as well, so we can change this from linear to log. So this means you've got 10 to the 0, which is 1, 10 to the 1, which is 10, 10 to the 2, which is 100, and so on. So these common options listed can essentially be programmed using a procedural command. So we can use title to create the title, and then we need to supply this in the form of a string. And we can specify the X limit. And if we have a look at its documentation, we need to supply a left value and a right value. So this is the lower and the upper bound respectively on the x-axis, i.e. the left value and the right value. We can set the x label and we can set the x scale. Now, because we're using the default, I'm just going to comment this out. So we can also do the same thing for the y-axis. And here, instead of left and right, we're going to use bottom and top. And here, we're going to set the y scale to log. So if I just type in exit, and now just go ahead and run the script file, notice that this plot displays with the specified options for the axis. I'm going to go to Tools, Preferences, IPython Console, Graphics, and change the backend to Qt. This will essentially be the default now when I restart the kernel. So here we can see we've essentially got the same plot that we had before, except this time we've programmed all the options instead of using the general user interface to update them. So now we can essentially change the properties of this blue line. So it's got a label, so let's just call it line plot. Let's change it to dotted. Let's change its draw style to steps mid, and let's change its width and its size. So once again, we can program all of this, and these are essentially supplied as optional parameters to this plot function. So what we want to do is supply a label. And then we can supply a line style. And this is going to be dotted. We can supply a draw style, which is going to be steps mid. Notice that I've got a dash here. We can supply a line width, which is 3. We can change the marker to be a star. And we can change the marker size to 15. So if I go ahead and run this, I get this unrecognized marker style, star. So I need to actually use the symbol star. Okay, so now that I've done this, I've essentially got the same plot that I had before. And if I go back into curves, notice that the color is listed using essentially 8 hexadecimal characters. So these are essentially corresponding to the red, green, blue, and alpha channel. And each of these is a numeric value from between 0 and 255, with the typical alpha value being 255, or FF in hexadecimal. So the hexadecimal values give you essentially the greatest flexibility to select a color. However, they're quite hard to remember. So what we have is this CSS4 colors dictionary. And notice that we've got a key, which is essentially an English color name, and the value is the hexadecimal value. So for example, if we have a look at the hexadecimal value of the color sea green and supply it, Notice that when we click out in the field, the FF is added for the alpha, and the color is what we would expect from sea green. So we can also use royal blue, and we can also use tomato. So just a quick note, Python generally prefers to use lowercase for a hexadecimal value, but they're listed in uppercase in the CSS for colors dictionary. Python will accept both, but generally a better practice is to use lowercase because that's what Python uses in its default representation for a hexadecimal value. That being said, the code is generally a lot more readable if you use the key name, so sea green, royal blue, and tomato are much more readable than the hexadecimal values. So as a user, you'll be able to recognize what sea green, royal blue, and tomato are. And if you type in a name that's not recognized, you're going to get an error, and this is shown in the console. And then black was selected by default when the string wasn't recognized. Okay, so now that we've got a basic understanding of color, we can assign it as an optional parameter within the plot function. So we're going to use the color sea green, and we're also going to specify the marker face color as royal blue, and we're going to specify the marker edge color as tomato. So now, if we just compare this menu left to right, we can see that we've got essentially all of the options that we changed programmatically supplied into this plot function. So let's now have a look at the colors that are available in CSS for colors. So what I'm essentially going to do is I'm going to create a for loop. So I'm going to go through each color in CSS for colors. So this will give me the key name, which I can then go ahead and print. So if I run this, I can see all the key names in the IPython console. So instead of printing the key name, I'm actually going to plot, and I'm going to plot no X data and no Y data. I'm going to specify the color, and I'm going to supply a label. And the label is going to be the color. And we're going to change the line width to be 5. And then we're going to add a legend to the plot. We're going to specify the number of columns in the legend. And we're going to specify the location of the legend being center. And notice I need to use the American spellings for color and center. So if I just maximize this plot, I can now visually inspect what each color looks like. And you'll have generally a vague idea of what these colors are because these are used in the English language. So notice one thing, that there's no spacing in any of the color names. So we can also have a look at the axis properties and then go to the curves, and then we can select the color that we want, and we can see what its hexadecimal value is, and we can see it as an RGB tuple. And notice that we've got more flexibility if we use the hexadecimal value, but the code's more readable if we use the subset of CSS for colors. We also have base colors, which are essentially red, green, blue tuples, normalized to 1. So these correspond to the primary and the secondary colors. So the primary colors are red, green, and blue. And then you've got the secondary colors, which are a mixture of 2 of the primary colors. So you've got cyan, magenta, and yellow, and then you've got black and you've got white. So each of these colors has a one-letter abbreviation, but because blue takes the character B, we use K for black. So if we have a look at this plot command, we've used essentially the long version of each of the optional parameters. And this makes the code much more readable. However, for convenience, there's a shortened down version of most of these parameters. And this saves a bit in the typing, but unless you're familiar with Matplotlib, the code becomes a bit less readable. And we can see with the abbreviated parameters that the plot essentially comes out as identical. So if I go ahead and have a look at a more simplified version, we've got the line style, we've got the color, and we've got the marker. And notice that I'm using the abbreviated version of line style, color, and marker. So what I can actually do is combine these together. And if I go ahead and plot this, notice that I get the same plot as before. So this is a shorthand way of getting the same thing, but it becomes a lot less readable. So now if I have a look at the documentation for the plot function, I can see that it can actually take multiple parameters. So essentially we can plot one or more lines. So we've got x, y, and then format, and then we've got the next x, y, and then its format, and so on. So I'm just going to vary the y values just by adding a constant offset. So the lines will generally have the same form, but they're going to be offset by 10,000 each. So let me just add in 4 lines. And if any of the parameters are supplied using a keyword input argument, it's going to essentially apply them to all of the lines supplied to plot. So if I go ahead and plot this, notice that we've got the 4 different lines. So each of these has a different color, a different line style, and a different marker as expected. So this multi-form of plot is essentially a quick and dirty way to create a plot with multiple lines. It's not as readable, and each line cannot be customized to the maximum extent. If you want to do this, then you can individually use plot for each line and specify each line's parameters. So I just want to remove the lock here so I can examine the draw style. So we see the default draw style, which is a line connecting the 2 points. And we can also compare what the steps do. So here we see the default draw style, the black line. So we basically draw a straight line between each marker. And here we've got pre, so we basically step up at this previous marker. And then we've got mid, we step up in the middle of the 2 markers. And then we've got post, and that means we post step up at the marker. Let's now have a look at creating a legend. So we've seen that we can use plt.legend. And because we've assigned each line a label, these labels are automatically used when the legend is created. So if I just comment this out and go back to the shorthand form, we don't have the option to specify the label here. So we need to supply it as an optional parameter to legend. And we essentially supply it as a list of strings. So here we can see the legend displays as expected. And quite often this will be done using a list comprehension. So here we see that we're using line for each line, so we can just have this string line plus the string of the number for the number in the range, and we're starting at 1 and going up to 5 but not including 5. So when we run this, we essentially get the same result as before. So this is a bit less readable, so I'm essentially going to change it back to what I had before. And if I just have a look at the parameters for the legend, I can see that I can also specify its location. So let me change this location to lower right. Okay, so now for simplicity, I'm going to go back to the plot of a single line. So let me just create a new script file. And let me just copy and paste the code that I need. So we've got our imports, and then we've got our X and Y data, and then we've got our plot. So let's have a look at this plot. So we've essentially got the same plot as before, except it's got a legend on it. So notice that the X scale is in linear and the Y scale is in log. And we can use the grid function to add a grid to it. So this adds a grid at the major grid lines. So if we highlight grid and inspect it, we can see that we've got these optional parameters. So we've got this optional parameter which can be used to select the major or minor grid lines. So by default, the minor grid lines are not shown, so this visible is set to false. I'm going to update it to true, and now I see these minor grid lines. And because the grid is essentially a line, it shares many consistent parameters to the plot function, which creates a line plot. So we can specify the line style, we can specify the line width, and we can specify the color. So it's done something a bit funny to my major grid line. So if I just go ahead and rerun this, it now displays as expected. We can turn the minor ticks on, and notice that this displays the minor ticks on the x-axis. So now we can set the axis to x, and we can add these as well. And now the plot looks like it's done on a piece of graph paper, and we can more easily identify where each point is. Okay, so now if I just create a new script file, and I'm going to have the same imports and the XY data, but this time I'm just going to create three separate plots, and I'm going to run the script. And notice I've got figure 1, I've got figure 2, and I've got figure 3. So every time I call plt.figure, I create a new figure. And by default, it's going to take the integer of 1, then the integer of 2, and then the integer of 3. Now, if I have a look at the optional parameters for figure, we see we've got this parameter num, and I can assign this to a different value. So notice that num's 10, and then we take 1 after 10, which is 11 and 12. So let me just close everything and run this again, and now we've got 10, 11, and 12. So we can close a figure using the X, or we can also do it programmatically by using the close function. So if I just highlight close and go ahead and inspect it to view its documentation, I can see that I can essentially specify a number, or I can specify the string all, which will close all figures. So let's close figure 10, and then let's close all figures. So plt.close all is quite commonly placed at the top of a script file after the imports to make sure that no previous figure that's been opened is going to be reselected and edited. When we run code in the IPython console, we'll essentially see the return value of the last function. If we don't want to see this, we can suppress it using a semicolon. And notice that no return value is shown in the IPython console. So let's create a new script file, and let's have a look at plt.subplot. So we've seen that the default value is 1, 1, 1. Let's change this to 2, 2, 1. And let me just open up a spreadsheet. So what I'm essentially going to do is I'm going to create a grid, and it's 2 by 2, and then we've got an index for each value. So 2, 2, 1 is essentially this. And let me just add some basic code for the plot. So let's create the figure with the subplot 2, 2, 1. And now let's have a look at 2, 2, 2, 2, 2, 3, and 2, 2, 4. And if we want to go back to 2, 2, 1, we can add another line to it. Okay, so that's a brief overview of procedural programming. So in procedural programming, we're essentially just calling a function, and then calling another function, and then calling another function. With Matplotlib and with Python in general, it's generally better practice to use object-oriented programming. So what I'm going to do is have a look at the same plot that we've made before, and I'm going to convert it from procedural programming to object-based orientated programming. So we've already got the object x and y, which is our data structure. We can assign the figure to the variable name figure. So let's go ahead and do that. So this is our figure, which is a blank canvas. And now what we're going to do is add an axis to the figure. So let's explore the figure in the Object Explorer. And essentially the figure has a number of identifiers. So we've got a number of methods that can be called from the figure. And here we see we've got methods to add a subplot or an axis. So let's use fig.addSubplot. And if we run this, notice that we've got an axis returned in the IPython console. So what we're going to do is assign this to a variable. And now notice that we've got axis display in the variable explorer. And we can view this with the Object Explorer. So now the axis has a number of methods available to it. And we can essentially call the plot from the axis. And then the axis plot method is consistent to the pyplot function plot. So we can use the same optional parameters. And we can assign this to the variable lines. And notice that lines is a list, and it's a list of line2D instances. So we can index into this list. Because it's a list of just a single line, we can access this single line at index 0. And we can assign this to a line, and we can have a look at its properties in the Object Explorer. So the axis has a number of get and set methods. And essentially, for the title and the label and the limits, we've got an equivalent set method. So let's just go ahead and update all of these. So we've essentially got a very similar looking plot to before. And the legend can also come from the axis. So let's go ahead and add a legend. The grid also comes from the axis. Let's go ahead and add a grid. So we've essentially got the same plot as before using object-oriented programming. Let's be militant and assign everything to a variable now. So assignment to a variable generally means that we can access the object again, and because we can access it again, we can go ahead and use its methods to modify it. So if we have a look in the Variable Explorer, we see that some of these actually have the return value none type. So there's no point in returning these. So these are essentially mutable methods that have no return value. And many of the set methods have a complementary get method. And this means that there's essentially no point in assigning these to a variable name either. So it's generally better to use this form when you're using object-oriented programming. So you're creating the figure, the axis, the lines. I'm taking one line from lines if you want, and you're creating the legend. So if I go ahead and exit and create a new script file, we'll continue from now on using object-oriented programming. So essentially what I'm going to do now is I'm going to create a line plot with a large number of lines. And I'm just going to use a positive step and also create a second plot using a negative step. So notice that we're using this default palette and that it actually repeats after a certain amount of lines. And if we have a look at the other plot, we can see that one goes from lower to higher and the other goes from higher to lower because the step is positive in the first case and it's negative in the second case. So notice in the code that I've not specified any colors, and what's actually happening is that Matplotlib is using its own default color palette. And we can change this using recall parameters. So let's have a look at the default recall parameters. So the recall parameters is essentially a mapping. So if I have a look at it in the Variable Explorer, I can essentially see the key value pairs. And if I use the function RC, I can essentially update one of the values using its key. And if we have a look at the keys, we can see that essentially some of the parameters are grouped using a dot. So this is similar to accessing an attribute from an object that it belongs to. So let's have a look at this axis.grid, and we see that it's got a default value of false. So let's select axis, and then we want to assign the grid to be true. And if we have a look at the grid itself, we can change its line style. So let's change it to a dotted line style. And then we've got some properties from the X-ticks. And if we want to have a look at the minor X-ticks, we can change their visibility to true. And we can do the same for the Y-ticks. So let me just now exit and recreate these plots. I notice that when I recreate these plots that the grid displays as expected, and also the minor ticks display. And if I have a look at the recall parameters, I can see that we've got this axis property cycle. And this is essentially used to change the colors of each line. So notice that it's of the type cycler. So let me just have a look at this in the IPython console. So we've got axis prop cycle, and it's a cycler instance that has the color and then a hexadecimal value for each color. So we're going to import the cycler class from the cycler module, and we're going to create our own colors. So let's just create the colors tomato, sea green, royal blue, hot pink, and cyan. And then let's just use the recall function to update the axis property cycle to these colors. So if we go ahead and run this, we can now see that we are using the colors specified. Let's open up the word processor and let's have a look at each of its colors. So we've got a hex value for each color. And with this, we can create a color scheme that's consistent to the word processor. So let's just create a standard colors dictionary. So the key is going to be the color name, and the value is going to be the hex value. And if we just get the values and cast this to a list, we've got the list of colors. So we can create our property cycle using these colors. And then we can use recall to assign this color cycle to the axis.prop cycle. So now the colors are consistent to the colors within the word processor, as expected. So let me just remove the recall parameters and go back to the default settings. So essentially when I replot this, I'm going to get the default chart that we had before. So Matplotlib has a number of pre-installed color maps, and it uses one of these in the axis property cycle. So if we type in plt.colormaps, we can see the names of all these color maps. And let's go ahead and examine some of these. So the function getColorMap can be used to retrieve the color map in the IPython console. And here we can see the colors. So if we have a look at this plot, and we have a look at these colors, we can see that they match. So if we wanted to change this color cycle, what we could do is use the colors attribute to access the colors here. So we see essentially we've got a normalized RGB tuple for each color. So essentially we would just use this for the color. So let's have a look at some of the other color maps. So let's have a look at Pastel 1, Pastel 2, Set 1, Set 2, Set 3, and let's just update this to Set 3. So let's close all figures and let's replot. So let me just comment out these strings. So now the plot is made using set 3. So previously we've looked at procedural programming and object-oriented programming. So let's just go ahead and create a plot using procedural programming. So here we don't have access to the figure. But what we can do is we can use the getCurrentFigure command to assign it to a variable. And now from the figure, we can access the axis. So we can use getCurrentAxis and assign access to a variable. So the figure has the axis attribute as well. So this is always going to be a list of axes, and we can assign this to a variable. So the axis has the attribute figure, and we can use this to get the figure. So this is essentially useful if you've created a figure using procedural programming and then you want to go ahead and access something using object-oriented programming. So let's now have a look at creating multiple figures. So instead of just creating one figure, we're going to create figure 1, figure 2, and figure 3. So let's go ahead and plot this. So we've got figure 1, figure 2, and figure 3. So because figure 3 is the last figure that's been created, it's the currently selected figure. So if we use getCurrentFigure, it's going to give us figure 3, and if we use getCurrentAxis, it's going to give us the axis on figure 3. Supposing we want figure 1 instead, well, what we can actually do is just use plt.figure, and we can supply it with the number of the figure, and this reselects figure 1. So therefore we can assign this to the figure, and then we can get the current axis. And then we can create another plot. And we see this works as expected. So I've created a figure and an axis separately using two separate commands. So we've got plt.figure and figure.addSubplot. Now, because this operation is so commonly carried out, there's actually a command that groups both of these together. and it can take in the optional parameters of each of the individual commands. So PLT subplots returns a tuple, and the first element in the tuple is the figure, and the second element is the axis. So this essentially works in the same way, but is a bit more succinct. So let's have a look at using this form to essentially create figures with differing amounts of subplots. So the default is essentially going to be a single subplot. We can create a plot with 2 rows and 1 column, another with 1 row and 3 columns, and another with 2 rows and 3 columns. So if I have a look at these plots one by one and have a look at the axis in the Variable Explorer, we can see that axis 1 is an axis instance. If we have a look at figure 2, we can see that axis 2 is actually an ND array of axis instances, and it's a 1D ND array. If we have a look at figure 3, we can see that axis 3 is also a 1D ND array of axis instances. And if we have a look at figure 4, we can see that axis 4 is a 2D ND array of axis instances. And so this means we can access the plot function from axis 1 directly. For axis 2, we're going to need to specify the index, and then we can use the plot function. So we can create a plot at index 0, and we can also create a plot at index 1. So for figure 3, we've got axis 3, and this is also a 1D ND array. So we can create a plot at index 0 and a plot at index 2. Okay, for axis 4, it's a 2D ND array. So we're going to need to index into both indexes. So we want to select the row first, and then the column. So in this case, we selected row 1 and column 2. And now we can select row 0 and column 1. And if we have a look at the plot that we created before using procedural programming, we can essentially recreate it using object-oriented programming. So let me create a new Python script file. So it's going to be the same at the top, the same imports and the same data. And just for clarity, we've created the figure and the axis separately. And then we went in and we've created a plot at each index. So we've got some other options to group the axes together. So we can create a mosaic. So the mosaic is essentially a list of lists. Generally, we would have this as a NumPy array. So we should be able to view this in the Variable Explorer. Now there's a bit of a bug and the strings aren't showing, so this is going to be fixed in the next version of Spyder. So I've submitted the bug here and they've actually already worked on fixing it. So we've got the figure method subplot mosaic, and we can create a mosaic from this NumPy array. So notice that 2 of the strings were identical, royal blue, and they're beside each other. So this is essentially an instruction saying that both of these subplots should be combined for the royal blue. So we've got Mosaic, but if we have a look at ax in the variable explorer, we see it's a dictionary. And the keys are the strings specified when we created the Mosaic. So if we index into the dictionary using the key tomato, we retrieve the axis, which corresponds to tomato. So we can go ahead and create a plot for each of these keys, and we can see that it works exactly as expected. So far, all of the axes that we've created have been on some sort of grid, so we've used some sort of subplot. What we can actually do is we can draw an axis using a rectangle. And just for convenience, I'm going to use a named tuple. And this is going to allow me to create this axis rect named tuple class, where I can specify the left, the bottom, the width, and the height. So this will make my code a bit more readable. So what we can use is figure.addAxis. And then we need to specify the axis in the form of a rectangle. So the expectation is a tuple of the following form, but just for convenience, I'm going to use this named tuple, and so we can see this is the left value, this is the bottom value, this is the width, and this is the height. And let's just change the face color to royal blue. So notice that when I run this, that the entire plot is royal blue, because this is 0 and this is 1. So basically we don't see the bit with the x-axis and the y-axis because we've made the box at the boundaries of the figure. So this will become a bit more clear when I add a second box. So this, we're going to have the left and bottom at 0.2 and the width and the height at 0.5. So essentially this takes up half of the figure canvas, but 0.2 plus 0.5 is 0.7. So the top right corner is at 70% of the figure. So let's move on to a new script, and instead of using the x and y that we used before, we're going to use theta. So we're going to use linear spaced angles from -2 pi to 2 pi, and we're going to have 100 of these. So remember, 2 pi is tau, and this is the circle constant. And then we're going to have y1, which is going to be the sine of theta, and y2, which is going to be the cosine of theta. So let's have a look at this plot. And if we just have a look at the x label, what we're going to do is we're going to have a look at its optional parameters. So we've got location. So by default it's center. We can move this to the left. And by default it's rotation 0, but we can change this to 270. So let's just change it back to the default. So we want the location to be center and the rotation to be 0. Now, assuming we want the Greek letter theta, what we can do is we can change a string. So we're going to make it a raw string, and we're going to enclose it in $signs, and then we're going to use the left slash to insert this character theta. So we can also do the same with y, except this isn't going to be a special character. But in both cases, we can see that the characters look different and they're shown in a mathematical context. So this uses Matplotlib's default rendering. We can use latex rendering by using the optional parameter used text and set it to true. Okay, so now let's update the labels. So we want the labels to also be in this format. So we want them to be raw strings. We want to enclose them in $signs. And then we want sine to be a function. And we want cosine to be a function. And then we want to insert the special character theta. Now, because these labels are basically supplied to the plot function, and it doesn't have the parameter use text, what I'm going to do is use the recall parameters for text and set use text to be true. So now any text in the graph will use latex rendering. So notice that this shows figure 1 not responding, and this is because this is a lot slower. However, the fonts now look like what you would see in a maths textbook. And if you're writing a document in latex, then it's going to be more consistent. So one thing you might ask is whether there is a what you see is what you get user interface for latex. And if we open only Office desktop editors, there's actually an equation editor. And this is very similar to the equation editor in Microsoft Word. So we can use this to construct a more complicated equation. And then we have the latex selected. And then we can view the current line in linear. And we can go ahead and copy this. So let's just set the title. So we want a raw string and we want the $2 signs. So let's go ahead and run this. So there's an error here. So some of the special characters might not be available. So let's just go back to the word processor and create something with characters that are used more commonly. So let's just create a fraction and let's just add some Greek symbols. And we see that this is latex and we can set it to be a linear. And we can go ahead and copy and paste this. So it needs to be enclosed in a $sign. And then we need the string quotations. And then it needs to be a raw string. So we can go ahead and attempt to run this. And now we see that this equation displays in the title as expected. So only Office Desktop Editors is a free Office suite available for all platforms, so you'll be able to use this on Windows and Linux. Okay, because the text rendering is slower, I'm just going to disable it and use the Matplotlib's default rendering. And this time I'm going to have a look at Y1, Y2 and Y3. So the sine and the cosine can be plotted on the same axis because they've essentially got the same dimensions. The tan, on the other hand, has different dimensions, but is related to the sine and the cosine. So in fact, the tan is the sine divided by the cosine. So what I'm going to do is I'm going to create a left axis. And this is essentially the same plot as before, except the axis has been renamed. So the axis has the method twinX. So we can create a right axis from this method. So here we've got the left axis. And we can add the plots to it. And we've got the X label and the Y label. So to the right axis, we can add a plot. So notice that the left axis and the right axis have different dimensions, but they've got a linked hex, as expected. So I can set a Y label for the right axis. So this is going to be Y3. So let's go ahead and insert a legend for each axis. So notice what's happened is that one of the legends has just been placed on top of the other legend. And this is essentially because the right axis is placed on top of the left axis. So fortunately, legend is both a figure method and an axis method. So if we use the figure method instead, notice that we've essentially grouped everything on the figure into one legend. So let's now have a look at the location of the legend. So just for simplicity, I'm just going to have a single subplot, and I'm just going to have a single plot in it. And I'll also add the grid. So here the location is chosen by default and it's on the top right of the axis. So we've already seen the location parameter. So for example, we can change it to the upper left, or we can change it to the center left, or the center, and the lower right. So I'm going to create a named tuple for convenience. So one's going to have an X and Y parameter, and the other is going to have an X, Y, width and height parameter. So what we can do is use the parameter bbbox to anchor. And this is essentially the boundary box. And we can change essentially the boundary box to be at a certain position on the axis. So notice that the axis occupies a certain component of the figure. So the figures has more canvas space than is occupied by the axis. So we can actually change the position of this boundary box to be outside of the axis. So here we don't actually see the legend. If we have a look at the figure properties and use the title layout, then we do see it. So it's sometimes quite common to use dimensions that are larger than the axis. So it comes out of the axis and displays on the figure. And we can use the figure method type layout to give it a tight layout. So for example, this might be a bit more convenient than having the legend display all over the data, particularly if the legend has multiple lines in it. So we can still use this black box to anchor when we are using the figure legend method. However, obviously if we set the parameters to be bigger than the figure itself, we can't go outside the figure, so they're not going to be shown. So let me just use my name tuple from before, just for convenience. So here the x is 0.5, the y is 0.5, and the width is 0.5, and the height is 0.5. So we are essentially taking this to the corner of the figure, and this is why it's shown in the top right hand corner. So we can understand what's going on a bit better when we change the x and y values. And as mentioned, if any of these dimensions is greater than 1, the legend's essentially going to be outside the figure canvas and we're not going to be able to see it at all. Okay, so just for clarity, I'm only going to have the sine and the tan plot. So the sine plot's going to be on the left axis and tan plot's going to be on the right axis. So let me just clear up the code. And what I'm going to do is change the color of the label so it matches the color of the line. So if I go ahead and run this, I can now see it's a bit more clear what axis each line corresponds to. And if I have a look at some of the identifiers of the left axis, I can see I've got this tick parameters. And if I press Ctrl and I in order to inspect it, I can see that I can select an axis and I can change the length and width of the tick parameters as well as their direction. And also the color properties can be changed. Okay, so now we see the changes are made to the left axis. So we can also access the spines of the axis. So this is an attribute, but if I highlight it and press Ctrl and I can inspect it. So each direction can be accessed as an attribute or via a key similar to a mapping. If I have a look at the directory of, for example, the left spine, then I can see that I can set its line width. And I can also set its color. So I've used a unique color for each element, just so you could see what was changing. However, if I set these all to royal blue, now it becomes clear that the blue line is associated with this left axis. And we can make similar changes to the right axis. And now it's obvious that the tomato line corresponds to the right axis. So this type of plot isn't too common. Generally, it's better just to use subplots, but it's a good example plot of going in and changing some of the properties of the spines and the X-text. So the figure has a save button, which can be used to save the figure to an image file. There's also the save figure method from the figure, which can be used to save the figure. So if I just have the file name image1.png, it's saved in the same folder as the Python script file. And we can also change it to another file format, such as a PDF. So these file formats are essentially images of the plot. So you'll not be able to go in and modify the plot once it's on this file format. So Matplotlib doesn't have a native file format for a figure. However, the figure is a Python object. So what we can do is import pickle, and then we can open a new file in write binary mode, and we can just dump this figure to a file. So now if we exit, and let's just create a new Python script. What we can do is import the libraries and import pickle. And we can open this file that we just created, this time in read binary. And we want to load this file and assign it to a variable figure. So we've got this figure and we can opt to show it. And we've got the figure back. So we don't have all the code that we used to run the figure, but we've saved this figure to a file and we've managed to reopen it. Okay, so let's have a look at just two simple points. So we want the 0.13 and the 0.26. And what we're going to do is just create a standard axis that's going to be in 2D. And we want to just plot this X and Y data. And let's just set the color to be royal blue, and we want to add a marker. And we can go ahead and set the label for each axis. So this should be the X label and the Y label. Okay, so what we want to do now is extend this to 3 dimensions. So if we do this, we want a 3D axis. So we use the keyword projection and assign it to 3D. So the 3D axis is essentially a child class of the 2D axis. So basically it has the same identifiers, but it also has supplementary identifiers which are used to handle the 3rd dimension. So we can use this plot 3D to plot to 3 dimensions. And instead of just having an X label, a Y label, we now also have a Z label. So let's just add the labels first. So we've got our X, Y, and our Z, and now we can add our line. And if we left click onto the 3D axis and just hold down and move our mouse, we'll see that the axis rotates. So we can essentially view this at multiple angles. And we can use the home button just to go back to the defaults. So if we have a look at its properties, we've essentially got additional properties for the third dimension Z. So the 3D axis is essentially a specialized type of axis. There's additional specialized types of axis, such as the polar axis. So what I'm going to do is I'm going to create a new script file. And I'm going to also import pandas as PD just so I can get data in the form of a data frame. So basically I'm going to have angles in both the degrees and radians. And I'm going to have values that are essentially in the XY coordinates. And they can also be expressed using an angle and a radius. So all of these points have a radius of 1. So a radius of 1 from the center, i.e. from the origin 0, 0. So what we can do is just create a normal plot. And we're going to plot each of these points individually using a different color. So if we have a look at this plot, we see each of these different points. So we can see that they've all got a radius of 1 from the center of 0, 0. And if we conceptualize this as being an angle, they've all got a different angle. So what we can do is set the projection to be polar, and we can have a polar axis. And instead of using the XY coordinate, we use the angle in radians and the radius. Although we use the angles in radians to actually perform the plot, the polar axis displays the angle in degrees. So you can kind of see what's going on by looking at the Cartesian and polar axis side by side alongside the data frame. We can use the axis method annotate to annotate a plot. So let me just inspect axis.annotate. And here we're going to get details about the parameters. So we've got the text and XY, and then we've got the XY coordinates. So the measurement system used for the XY coordinates can be data. So that's going to be the data, or it can be the normalized axis or the normalized figure. So let me just use the same values just on the different coordinate systems. So that's the data, that's the axis, and that's the figure. So here we've just annotated the figure using some text. And we can change the color of the text as well. So generally an annotation will involve an arrow. So you're going to point to something on the figure, and then you're going to have some text that describes the thing that you're pointing at. So what we have is this arrow props dictionary. So recall a dictionary has key value pairs. So normally in Python we would use a dictionary in the following way, i.e. using the braces. However, the dictionary can be instantiated using the dictionary class. So one of the advantages of using the dictionary class is that it essentially uses the same syntax highlighting as the parameters for a function call. So what we're essentially doing is we're grouping all the parameters related to the arrow and assigning this to arrow properties. So essentially when a function has a large number of parameters and we want to further group these parameters, we can use a dictionary to do that, and it becomes clear that we're doing this using the dictionary class opposed to the braces. So we can change some of the parameters of the arrow. So we've got a fancy arrow or a simple arrow, and we can change the colors of the arrow. We can use get properties to get the properties of a Matplotlib object. So we can get the properties of the figure, and we can get the properties of the axis. We can get the properties of this line list. And we can also get the properties of this single line in this line list. So we also have the set properties where we select an object, and then we select a parameter, and then we can assign it to a new value. And most of these parameters we've seen before because we can assign them to optional parameters when we use the plot method of the axis. So we can make the following changes. And let me just use the shorthand form just for convenience. So there are some less commonly used parameters, such as the film style and the marker face color alternative. So basically the marker face now has two colors. And this will become just a bit more clear when I change some of the size parameters. So you can see the difference when I change the fill style from top, right, left and bottom. So if we go back to the notes we took, notice that there is a large number of plot types, and so far we've only really explored one plot. Let's have a look at some of the other plot types now. So let me just create a new Python script file. And I need to import the libraries. So I no longer need pandas. And I'm also going to import the CSS for colors because I'll use these in a moment. So what I'm going to do is create a simple NumPy array. So it's going to increase from 0 to 50 in steps of 1. Y is going to be x squared, and then S is going to be y plus 1. And I want to list the CSS for colors. And I want to take 50 random CSS for colors. So I'm also going to need to import the random module. So essentially I've got an X and Y as before. So Y is going to be plotted with respect to X. S is going to be the size. So this is going to be the size of each point. And then we've got color, and this is going to be the color of each point. So let's now have a look at the scatter method. First of all, I need to create a figure and an axis, and this is just going to be the same way as before. And now let's have a look at the axis method scatter. So we need to specify X and Y values. And we can also specify the size and the color. So notice that the 4 of these are all plurals. And we get a path collection. So every single point is increasing in size as we go from left to right, and also has a different color. And if we have a look at the properties of the path collection, so I shouldn't have the percentage sign there. So notice that some of the properties are singular and some of the other properties are plural. So this changes the way that the property works. So is it going to be unique for each point, i.e. singular, or is it going to be plural, so each point will have a different property? So notice we've created a figure and an axis in the exact same way as before. And we can customize the axis using the exact same way as before as well. So let's just add an X label, a Y label, and a grid. So here we went for the plural version of X, Y, size and color. But notice that we can set a singular size and we can set a singular color. And notice that the documentation says if you want a singular color, prefer to use the color parameter opposed to C. So the color parameter is going to expect a single color, whereas C is going to expect a vector. So notice that each point now has a single size and a single color, and this plot is shown above the previous plot just for convenience. So we can also change the line width, and notice that this time the line width corresponds to the line width of the point. And notice that I've used a singular term, so this has changed every single point. Okay, so let's go back to the random colors, and let's also have random edge colors. So here I should be using C instead of color, but the code still works. So we've got the line width, and we're going to have this as a function of X as well. So we can set the marker. Now this is singular, so it's going to apply to every single point. The scatter method doesn't accept a plural version of markers. So let's get a bit more details about the markers. So the scatter function doesn't tell us about the available markers. It says see matplotlib.markers for more information. So let's go from matplotlib.markers and let's import marker style. And if we have a look at marker style, we can see that we've got the attribute markers. So this is essentially a dictionary, and it tells us the supported markers. So what I'm going to do is just comment out the following. And I'm going to use set P to set line width to 0. And then set the marker. Okay, so this doesn't allow changing the marker. So some of the properties are a bit limited with get properties. Okay, so what I'm going to do is I'm going to have a look at this marker dictionary. And what I want to do is get the keys of the dictionary. So let me just assign this to a variable markers. Let me just fix the formatting quickly. So if I cast this dictionary into a list, I'm going to take the list of the keys. And I'm going to add a new axis. So let's just set the marker to be marker. And let's also have the variable num and set this as an offset. And let's just increase num by 100. So let's run this for loop. Let's just remove the color. So we're using the default colors. And let's now examine this. So I want to reverse this. And recall that reverse is a mutable method. So let's reverse this. And now let's zoom in. So now we can see what each of the markers looks like. And because it's reversed, the marker on the top is going to be the marker that's at the top of the markers dictionary. So here we can see what each marker looks like. Okay, so moving on to a new script file. I'm going to load the imports and I'm going to create X and Y data and plot it. So this is just a sine and a cosine plot as before, except the amplitude has changed. We can plot a series of vertical lines using V-lines. So once again, we should be careful here to see what's plural and what's singular. So X is going to be plural and Y-min and Y-max are going to be singular. So let's create the X data and let's create Y-min and Y-max. So let's just set the color to be tomato and we can set the line width and the line style. So in addition to V-lines, we have the axis horizontal line. So this is used to just insert a single line along the axis. So because this is a single line, everything is singular. One thing to note is that Xmin and Xmax are using axis coordinates. So these are normalized between 0 and 1. Whereas the Y is in terms of data coordinates. So we can have a look at the variable V-lines and the variable AXH-line in the variable explorer. So notice that this is a line 2D and this is a line collection. So if we have a look at properties of V-lines, notice that many of the properties are plural, such as colors. So what we can do is set the colors of each line to be an individual color. So this is going to be expect a list of colors. That's the length of the number of lines. So for example, if we go for magenta, yellow, magenta, yellow, magenta. Okay, so the visibility of yellow is not so good, so let's just change this to orange. So likewise, we can have a look at the properties of the AX line. So notice that the property color is going to be singular because there's only a single line. So we can set this to cyan, and we can also change the line width. And notice that line width is also singular. So we've had a look at V lines and AX H line. There's also H lines and AX V line. And the behavior of these is pretty consistent to the counterparts that we've examined, so I'm not going to have a look at these in any detail. So let's move on to another Python script file now. So I'm going to have a look at a bar graph now. So basically, at certain x values, we've got bars that are specific heights. So the x values and the heights are plurals, and we can also set an optional width, and this is going to be singular and apply to each bar. So let's have a look at the documentation for the axis method bar. So we've got x, and then we've got height, and then we've got the optional width, and notice that width is set to a default value. So if it's not specified, it's going to be 0.8. So if we supply x and heights to bar alongside the width, and just assign the return value to bar, we can now see each of these 5 bars. And if we have a look at bar in the Variable Explorer, we can have a look at its properties. So one property it has that we've not seen before is hatch. So I'll have a look at this later. First of all, I want to just explore width in a bit more detail. So I'm just going to create 2 subplots. And this time I'm going to create plural widths. So in this case, each bar is going to have its own width. So now we can see that each bar is now unique and has a unique width. So this is less common for a bar graph, but width acts as a plural or it acts as a singular value. So now I want to explore the optional parameter bottom. So I'm going to create a single subplot with 3 bar graphs on it. So the bottom of the second one is going to be essentially the height of the first one, and the bottom of the third one is going to be the height of the first one plus the height of the second one. So this allows us to create a stacked bar graph. If instead of a stacked bar graph we want to display the bars side by side, what we can do is use the width. So this time we're going to set the width as 0.2 as a singular value. And basically every x position we're going to offset by this width. So now we can create our bars using the different x values and the different heights and the constant width. So now the bars are side by side as expected. So we can have a look at the axis attribute, x-axis. And from this, we can have a look at the method getTickLocations. And if we want these in the center, we can change them to the x2 values. And we can also update the tick labels. So now it's group 1, group 2, group 3, group 4, and group 5. So let's go back to a simple bar graph. And let's have a look at the attribute patches. So if we view bar in the Variable Explorer, we see that each bar is a rectangle. So patches is plural, so we can access each patch using its index. So bar patches 0 is going to be the patch for the first bar. So if I have a look at the properties of patches, it's going to essentially give me the options that I can change, and this will change all 5 bars. However, if I just access a single bar, I can once again access its properties, and I can individually update each bar. Okay, so let's now explore hatching. So a hatch is essentially a pattern of the bar. So let me just update the plot. So I've got 2 bar graphs, and there's more bars in each bar graph. So we can specify the hatch style using the following strings. So these are singular strings. One thing to note is that when you use the left slash, it indicates that you're inserting an escape character. So 2 left slashes means I'm inserting an escape character, and this escape character to be inserted is the left slash. So we can also double up each of these hatch styles. And now I'm essentially just going to use a for loop to update each bar in the top one by one. And then do the same for the bottom. So the only difference between the top and the bottom is we're using the double versions of the hatch styles in the bottom and the singular versions at the top. So when we had a look at the stacked bar graph and we had a look at the side-by-side bar graph, we've seen that each set of bars were essentially grouped. So if we go back to this, we can change the edge color, the width, and the hatch. So the first group is going to use the hatch of X and the color sea green. The second group, the hatch of dot and the color royal blue. And the third group, the hatch of plus and the color tomato. So we can also create a horizontal bar graph. So the syntax is very similar, except you're swapping the height and the width. Sorry, this height should be 0.2. And we've essentially got the horizontal equivalent to the bar graph that we just had. So another plot type closely related to the bar graph is the pie chart. So what I'm actually going to do is just plot a bar graph and a pie chart together side by side. So first of all, let's just have a look at the axis method pie. So the pie chart just essentially has the heights of the bars. You don't have any X index. You just specify the order of the bars. So as mentioned, let's create a bar graph at the top. And let's just have this bar graph so each bar is customized. So now let's have a look at creating a pie chart. So we're essentially going to use the same heights here. So x2 is equivalent to what we had as the heights in the bar graph. And wedge properties is a dictionary grouping all the properties associated with the wedge. So here we can set the edge color and the line width. So generally the bar graph is preferred over the pie chart because it's more clear and you can compare each bar side by side more clearly than you can within the pie chart. The pie chart also has the option to explode each pie segment. So exploding essentially means you drag it away from the center. So let's have a look at different values of exploded pies. So this is brought out by 0.2 and this is brought out by 0.4. So you can see as the value increases, the more you bring it out of the pie. So as mentioned, the wedge properties groups the wedge properties together in a dictionary. If we have a look at pi, we can see it's a 2-element tuple, and this consists of 2 lists. The first list is each wedge, and the second list is the text at each wedge. So we can get the properties of a wedge by indexing into pi at index 0 and then indexing into that list at index 0. So the pie chart can also be modified to make essentially a donut. So let me just take the hatch tiles and the colors that we want. And this time I'm just going to create a single bar graph. So we're going to have an inner pie. And here I've set a radius of 1.5. And the wedge props has a width of 0.5. So you're essentially going to go from 0 to 1.5 and then have a 0.5 width. So going from 1.5 to 2.0, where the center is 0, 0. So using donuts in the form shown can also be misleading. So each of these segments is essentially the same size, but the smaller radius looks smaller just because of the way it's drawn. So in most cases, you're going to want to preference a bar graph opposed to a pie chart because it's a much clearer way to see the data. So we also have the axis method hist, which can be used to create a histogram. And a histogram is essentially a bar graph. So you have a NumPy array of x values, and then you're going to histogram these into bins. So for example, let's have 10 bins, and the start bin is going to be 0, and the stop bin is going to be 10. So let's histogram the x array over the specified number of bins over the specified range. So here I'm using keyword input arguments. One thing to note is that the axis method hist has the optional parameter range, and this is a Python keyword. So that's why this is highlighted differently. Within the function, it acts as the parameter and not as a range object. Since the syntax highlighting is making the code a bit more confusing, I'm just going to specify these positionally. So let's just add a grid and add the labels. So let's have a look at hist in the variable explorer. So we've got a 3-element tuple. So notice the first has a size of 10 and we've got 10 bars. So this is the height of each bar. The next has a size of 11 and this is because it's the boundaries of each bar. So because there's 10 bars, we need 11 boundaries because each bar has a start and a stop. And then the third element is the bar container itself. So this is essentially a bar graph, and if we have a look at the properties of this, we see that we get the same properties that we had when we had a look at plotting bar graphs. So now I want to have a look at the effect of bins. So I'm basically just going to use a for loop to plot out 3 separate subplots. And I'm going to change the hatching and the color. And otherwise, I'm just going to change the number of bins. So here you see when we've got broad bins, we don't really see the shape of the distribution. And when we've got appropriately sized bins, we begin to see the shape of the distribution. And when our bins are too finite, then we begin to lose the shape of the distribution again. So the number of bins will depend on your data and how much data you have. Let's import statistics and let's have a look at the median of X. So we see the median is at 6 and we can have a look at its quantiles. So this is essentially going to give the standard deviations around the median. Sorry, this should be a string. So we've got the standard deviations around the median. So we can represent this data set using a box. So if we have a look at the axis method box plot, we can see that we can essentially represent a distribution this way. So here we see the median and we see the standard deviations, and then we see the whiskers taking us to the minimum and maximum value. And if we open up the Variable Explorer and have a look at the box plot, we see that this essentially consists of line 2D plots. And you can see this because we've essentially got lines drawn on the axis. So instead of just having a look at the distribution of one distribution X, we can have a look at the box plot of some distributions side by side. So we're going to need to provide this as a list of distributions. And here we've got X and then X plus 1 and then X plus 2. So the box is a very basic representation of the distribution. We can also create a violin plot. So instead of representing the distribution just by using a box, we essentially represent it by using a KDE. So think of this as the histogram on its side. So this shows what the distribution looks like. So let's just plot the box plot and the violin plot side by side using subplots. So you can see that they're giving essentially the same information, but visually you can see what the distribution looks like more with the violin plot. So it's also possible to create a 2D histogram. So when we created a 1D histogram, we had X, and for a 2D histogram we need X and Y. So let's have a look at the axis method hist2d, and if we inspect this we can see that we've got the parameters X and Y, and then we've got bins. So let's just create the following X and Y values. And then let's just create bins that are 3 by 3. Okay, so now let's use this histogram 2D. So the Z axis in this case is going to be the C axis, which is the color axis. And basically this value of 3, 1 occurs the most times in this histogram data. So that's why this is the brightest, because this is the most populous point. And the dark squares don't have any occurrences. And then the other colored squares have a few events. So we use color to represent the three-dimensional nature of this data set. So we also have Hexbin, which is similar to a 2D histogram, except the shape is a bit different. It's hexagonal instead of squares. Okay, so one of the parameters is wrong. So instead of bins, I should have grid size. So let's just set the grid size to be 3. Okay, so this is essentially another way of representing the same data that we just explored. Alright, so let's now have a look at creating X, Y, and Z data. So I'm going to create a row using numpy.linspace. So I'm going to go between -2 and 2, and I'm going to have 11 values. I want this to be a row, so let me just use numpy.newAxis and create a row. Okay, so I want a similar thing in Y, but I want Y to be a column. So I'm just going to use the same values. And now if I view Y in the Variable Explorer, I can see that this is a column. So next, I want to use Meshgrid. So I want to basically project every X value along Y and every Y value along X. So here we need to supply the X row and Y column, and the return value is X as a matrix and Y as a matrix. So if we open up X matrix, we can see that every row is the same. So the row X is unchanged. We've just essentially expanded it along this axis. So now every single Y value has a corresponding X value and so on. So both of these are now the same dimensions. And what we want to do now is create some sort of function involving X and Y. So we can do this with a lambda expression. So we've got the input arguments X and Y, and then we've got some mathematical expression, which is going to create a Z value. So recall that a lambda expression is essentially a function. So these two are equivalent. The lambda expression is more convenient because it can be expressed on one line and used anonymously. So here, what we're essentially going to do is call the function, providing the X and the Y data. So this should actually be the matrix X and the matrix Y. Now, because we are only using this function once, what we can do instead of assigning it to a variable is that we can just call it and supply the parameters. And this gives us the Z matrix. So notice that when we open this up in the Variable Explorer, we've got a background color and we can already vaguely see what the shape of this distribution is. So some functions will require the matrix to be flattened. So we can use the ND array method flatten to flatten X, Y, and Z. So now we've got an X, Y, and a Z value. And each of these is a one-dimensional ND array. So let's now have a look at the axis plotting method matrix show, which can be used to display a matrix. So this is basically similar to how Spyder is going to display a matrix by default. So notice that the required input argument is the matrix, and this is going to be the Z matrix. So one thing to note is that although we have the X and Y values, this matrix is just going to display using its index. So this is the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's shown in the Variable Explorer for this specific matrix, and is unrelated to the X and Y vectors. So just for clarity, I'm going to add column and row for the X label and Y label. And let me just move the position of the X label to the top. So if you have a look at this figure and you have a look at Z matrix in the Variable Explorer, you'll see that it's essentially the same kind of color pattern. So in addition to the matrix show, we've also got pcolor. So matrix show will essentially plot a matrix, and it will always show the index, so the row and the column. Pcolor looks similar, but notice that we can specify X, Y, and the color Z values. So if we use pcolor and specify X mat, Y mat, and Z mat, then this time the X label is going to be the X value and the Y label is going to be the Y value. So recall that we had these ranging from -2 to 2, and that's what we see. So the Z data is shown using a color, and we can see what values these colors correspond to by using a color bar. So here we need to specify the mappable, so that's going to be pcolor, and then we need to specify the axis. And then we can optionally add orientation and location. So let's set the orientation to vertical and the location to the right. So here we can now clearly see what each of the colors corresponds to numerically. So we can also supply the optional parameters Vmin and Vmax. So this allows us to zoom into a specific range. So for example, if anything below 0 is classified as noise, then you might want to set Vmin to 0. And if we want to examine the noise in more detail, then we might want to set Vmax to 0. And if we want to have a look between 0 and 1, we can set Vmin and Vmax. If we have a look at the function plt.colormaps, we get a list of the color maps. So we've had a look at color maps before, and we focused on the qualitative color maps for the purposes of making line plots where we wanted each line to be distinct from the others. For this kind of purpose, we generally want a sequential or diverging color map. So we can see the overall pattern of the data and what values are lower and what values are higher. Just for convenience, I'm just going to create a for loop, and I'm going to create a new plot using the color map, and I'll just set the title of the plot to the name of the color map. So Matplotlib has a large number of color maps, so this is going to create a lot of plots. So I'm just going to scroll through these one by one. So here you can see the sequential color maps, and you can see how the pattern changes. When you don't really see the pattern at all, that's because you're using a qualitative color map. And qualitative color maps are designed for a different purpose, not for visualizing data using the color axis. So recall, for example, that we used the tab and the set color maps to change the color of the lines, and in that case we wanted each line to look unique. Okay, so now we've had a look at essentially all the color maps. Let's have a look at applying these now. So let me just close all these figures down. And let me just save the script file and create a new script file. So what I want to do now is plot 4 figures. So notice that when I'm using pcolor, I can specify the color map. So we can specify the color map using the optional parameter cmap within the function call. And this updates just that specific plot. If we instead use the pyplot function, which essentially corresponds to the name of the color map, this updates the recall parameters. So notice that the remaining plots, figure 3 and figure 4, were each using the color map magma, and that's because we updated the recall parameters. So let's just change the recall parameters back to the default, which is this Viridius. And now let's look at some subplots, and we're going to compare some of the more commonly used color maps. So essentially we're going to use the default, which is going to be Viridius. Another commonly used color map is Jet. We've also got Bone. And then we've got Hot. So these are all representing the same data, and the choice of the color map is essentially subjective. Generally, you want to pick a color map that best shows the contrast within your specific data set. So in addition to p-color, we have p-color mesh. And there's not a huge amount of difference between p-color and p-color mesh. The p-color mesh is essentially just more optimized for larger arrays. So here, instead of just having 11 points, 11 by 11, we're going to have 1001 by 1001. So we're essentially going to have more than 1,000,000 pixels. So let's have a look at p-color mesh, and we can see that its parameters are pretty much consistent with p-color. So we see a lot more resolution in this image because we've got a lot more data points. If we have a look at the properties of p-color mesh, this actually takes a long time to load on this older computer. And this is because there's so many data points in the p-color mesh. Let's have a look at other ways of representing this data. So instead of using p-color or p-color mesh, we can represent the 3D data using a contour. So contours are quite commonly used in ordnance survey maps, for example, denoting the height of a hill or a valley. So we've got the option of a contour or a filled contour. So we'll just create two subplots and have a contour at the top and a filled contour at the bottom. So basically we want the X, Y, and Z data, and then we want to specify the number of levels. So let's just set the X label and the Y label. And here we can see the height denoted by the contour. Okay, so let's just simplify the plot, and this time we're just going to have a look at a contour. So we want to customize the plot. So notice that we've got a lot of parameters here. So let's have a look at customizing the line widths, the line styles, and also the colors. So here we're going to supply the X, Y, and Z data. The levels is going to be 9. Notice that we've actually provided 11 values for line widths, line styles, and colors. So we only show 9 of them. The last 2 we don't show, but we need to specify them. So let's now create the plot. So now we can see that values below 0 are royal blue, values above 0 are tomato, and values that are 0 are black. So we've also got the axis method cLabel, which essentially labels the contour. So it's contour label, not color label. So we specify the contour, and then we want to specify the levels. So the levels of the labels can differ from the levels of the contour lines. If not specified, the levels of the contour lines will be used. So we can also change the font size. So let's change the font size to 12 and to 24. So I think 12 was best for this example. Okay, so let me now just change this to 12. So now visually I can see the pattern of the data, and I can also see the heights of each of the contours. So we can have a look at the properties of the contour plot, and we essentially see most of the parameters that we can supply as optional input arguments to the axis contour method. So color is one way of representing 3D data. We can also use a 3D axis. So let's just change the projection to 3D. And here we've got the 3D axis. So the 3D axis is based upon the 2D axis, so it's a child class. So it inherits essentially all the methods of the 2D axis, and it has additional methods that give it 3D functionality. So you'll see additional methods related to Z. Okay, so in the IPython, when I'm trying to inspect this plot 3D, it's not working, and it's just giving me plot. So this is probably just because of the way this has a case of 3D. But if I use the question mark in the IPython console, I'll get the details. Let me just add the X, Y, and Z labels. And now let's go ahead and add this 3D plot. So let's just specify the X, Y, and Z data and plot. So what we can essentially do is use the mouse to navigate around the plot, changing the angles. So the plot 3D is actually kind of hard to visualize. And as a consequence, there's two related plots. There's essentially the plot surface and there's the wireframe. So essentially each data point is represented using a square, and for the surface the square is filled, and for the wireframe the square is not filled. So the wireframe is sometimes a bit better when it comes to viewing the structure of the surface. So notice that when I spin this around, you can see kind of the top and the bottom. So we've essentially got three angles: the elevation, the azimuthal, and the roll. And we can use the axis method, set elevation, to update these. Notice that we need to refresh the figure using figure in the IPython console in order to update it. So what I want to do is explore these angles in a bit more detail. So let me just create a new Python script file. What I'm essentially going to do is create a 3D plot. So in the exact same way that we created one before, we're going to create the figure. Next, we're going to create an update function, and we're going to assume that this update function takes in a frame. So let's just specify what to do if the frame is below a certain value. So let's just set the title to include the frame, and essentially we're going to set the elevation, azimuthal angle, and roll angle, and we're going to vary the elevation angle. Then we're just going to set this to a fixed size, and then we're going to vary the azimuthal angle. And then finally, we're going to set this to a fixed angle, and then we're going to vary the roll angle. So basically we're going to see what happens as we rotate each of these three angles. And we're going to create an animation, so we need to import the function animation function from the Matplotlib animation module. So here we require the figure, the update function, and we need the frames. So the frames are going to start from 0 and go up in steps of 1 to 1081. And I'm going to set the interval to be 10 frames per second, although I've sped up the video recording a little bit as well, so you'll see this in slightly faster than 10 frames per second. But essentially you see what happens as you rotate each of these three angles. So the animation's pretty neat and we can save it. So we can save it to an image sequence using the file extension GIF. And it's actually going to play through the sequence while saving. So it appears to freeze while it's doing this. We can also save it to a video file. And here we need to specify the frames per second, again as 10. Otherwise, it saves a video file, but it doesn't quite play at the expected frame rate. Okay, so if I exit now, I want to just have a look at these 3D plots again. So we can essentially use these 3D plots with a color or a color map. So plot 3D generally takes a color. Plot surface can take a color map or a color. And plot wireframe generally takes a color. So let's just plot these four side by side. And here, you can see that that's a bit harder to view. This is easier to view. Now it's got a color map. And now we see the surface has a constant color and the wireframe has a constant color. So we can also add an image to an axis. So I'm just going to go into the folder that I'm working in and create this subfolder images. And I'm just going to have a look at this nature.jpg file. So to the top we see we've got blue sky, and then we've got clouds, and then we've got green grass. So if we open this up in an image manipulation program like Paint and select the color picker, we can see each pixel has 2 hexadecimal characters corresponding to red, 2 corresponding to green, and 2 corresponding to blue. Or we can represent these as a red, green, blue tuple. So the pyplot function image read can be used to read in an image, and it'll get stored as an ND array. So here we want to use a raw string, and then we want to specify the folder, which is images, and then we want to specify the file, including the file extension. So let's just assign this to image, and we can have a look at image in the variable explorer. So let's change the axis to 2, and now we've got the red values. So let's just open up Paint and have a look at the color picker. So we can see that we're essentially in the blue corner, and we've got the red value, the green value, and the blue value. And we can see that each of these neighboring pixels essentially has a very similar value. And that's why the top of this image is essentially appears to be the same color. So if we just take these values and have a look at the hex versions of them, what we essentially do is get rid of the OX and then replace the first OX with a hash. So this should actually be 236. And then this is going to be the exact same value that we see in the image manipulation program pane. So let's just create a figure and an axis. And let's just plot no data and set it to be this color and call the label this color as well. And we want to center the legend. So we can see that this is sky blue as expected. So let's go back to creating an axis, and we can display an image using the axis method image show. So there we go, the image displays, and you can see the large number of pixels in X and Y. So previously we had a look at the Cartesian axis, and we had a look at the polar axis. So what I'm essentially going to do is just create a new script looking at this previous data. So recall we had this data frame, and the data frame is essentially a table. So let's go back and plot the Cartesian axis and the polar axis. And what I want to do is just add this table to one of the other subplots. Okay, so let's just call this additional subplot axis table. And in this case, we don't want to see the x-axis or the y-axis. So let's just get rid of these. And also, we don't want to see the frame. So we have the axis method table, which can be used to insert a table. So notice that the parameters are actually using camel case instead of being all lowercase, like most other things that we see. So we want to specify the cell text in the form of df.values, which is essentially a list of lists. And we want to specify the columns in the form of df.columns, which is essentially a list of the column names. So we can now go ahead and create this table. Now, unfortunately, the default settings don't seem to be very good. So I want to disable this auto set font size setting. And then I want to set this font size to something that's a bit more readable. So now we've got the table and these two plots. Okay, so just to finish up, we've already had a look at recall parameters. So we essentially specify the recall parameters we want at the start of our script file, and then we run our script. We can also have a look at this Matplotlib file name, and this is essentially our configuration file. So if we go ahead and open this configuration file up in Notepad, it says note for end users, do not edit this file, and it says do not edit. So essentially if you want to use it, it's telling you to copy to Matplotlib's configuration folder within your user profile. So this is my user profile.matplotlib. So if I go ahead and copy this file, and let me just open it in Notepad. So now that we've went through most of the library, most of these settings will make sense to you. So I advise copying the setting you want to change below where it's listed, and then uncommenting it out and setting the setting that you want. Doing it this way means you've got the old setting above, so if something goes wrong, you can see what the default setting is and quickly revert back to it. So let me just change some of the settings relating to the grid. And I'm also going to add a marker by default. And let me just change the grid color. So let's just make it sky blue just because we have this. So let me just create a very simple plot just for demonstration purposes. So this is using the original default settings. I think I'm going to have to close and relaunch Spyder in order for it to view the updated Matplotlib configuration file. So let me now just relaunch the script. And now you see that we are using the settings in the updated configuration file, the grid shown by default, and we're using a dotted line with the markers as specified.